Hey, everybody. Sorry for being slightly late. Um, Unfortunately, I had to go out of town for a family emergency, but we're going to try to maintain the same schedule and pace. So this is highly experimental here. If things aren't clear or I don't sound clear, please let me know right away. Okay. Um, so is this readable? Does this read to everybody? It's super blurry. Okay. Um, okay. Okay. Let's try to zoom in and enhance. Is that better by any measure? How is the resolution there? Okay, so Keenan says that it's going to be blurry no matter what, huh? Okay. Um, well, okay. So it's readable. Okay. So after this lecture, if it turns out that things are not the best resolution or readability, I think what I might have to do is record during nighttime hours and then just field questions as you have them when you watch them. Okay, so let's just try this, and if it doesn't work out well, we can all reassess together and decide what's best. Does that sound reasonable to everybody? Okay, yeah, I apologize for this. I'm sorry. So first and foremost, let me ask, how did the exam feel? How did it go for everybody? Exam 3. What were any feedback on exam 3? Nothing in particular. Okay, so harder than 1 and 2, but not impossible. Okay. So
Yeah, there's some questions that felt like they weren't really on the practice exams, but they were feasible, but not as much preparation.
I see. Okay. So sorry, I just I'm not sure why. Let me change my view here.
Professor, it kind of felt like there were like one or two questions where we learned the concepts separately, but the question asked us to put them together, but we didn't really learn how to apply like the concepts at the same time for a specific question.
Okay.
Because like I remember there was one question where it was asking us to find the glide reflection given a half turn and a reflection versus just a reflection and a reflection, and that was like a little bit confusing for me at least, something like that. So, but it wasn't impossible. We just had to kind of reason it out for a lot of the questions. But I think we could have talked about the combinations of the topics a little bit more. That's all.
Okay. Okay. Yeah. And this is why I hope everybody saw the announcement that the fourth exam will be pushed back a little bit, just so we have some more time. I know we've been covering roughly a chapter per 2 times we meet, but the material that we're going to start going over after we finish chapter 9 is going to be, as I said, more applied, but also more challenging. So I want to give us ample time to like get comfortable with the material. So hopefully pushing the exam back will mitigate that feeling a little bit. Okay. So I know that as Keenan was just saying, you know, there's a lot of specific applications that we didn't go through, and that I was hoping that you all had the tools to be able to puzzle that out. But my anticipation is that exam 4 will not go that same way. Okay. In other words, I'm hoping that it will we'll be able to do more examples together, and it will be more example driven because now we're getting into specific applications of all this machinery that we've built. Okay. And by the way, I anticipate having all your exams graded and commented and returned to you before class tomorrow. Okay. So yeah, again, sorry that we're in this bizarre lecture circumstance, and that also I'm only halfway through looking through your exams, but by tomorrow it should be all set. Okay. So right. I just want to finish up. Remember, at the end of last lecture, we talked about the equation for a rotation in general. And I told you we were on this analytic detour, right? Where we would come up with equations for isometries at large, any isometry. So I just want to finish that up, and then we'll start talking about the reasons why we build all this machinery, how we get to classifying a finite number of groups that describe, for example, as I said at the beginning of the course and have reiterated, the types of wallpapers you can have. But we'll start a little more simply than that. We'll start by describing how a two-dimensional strip of pattern can have symmetries. The different groups that, if we're not concerned with filling the plane like a wallpaper is, right? Like, you know, when you put up wallpaper, the plane is the entire wall that you're applying the wallpaper to. We'll start a little more simply and just say, like, okay, what if we just want to look at the top strip? What if we just want like a thin roll of wallpaper that just goes along the top? Okay, that will dominate the lecture today. But before that, we should finish up talking about equations for isometries in general. Okay, and you know, we've made such a to-do about classifying different isometries and how they behave. I'm sorry, I just there we go. I just wanted to make sure the recording has the board in full. Okay, so we've made such the to-do about the way different isometries behave and how we can factor them, right? So what I want to do now is tell you the surprising result that isometries in general have a very simple form analytically. That is to say, the equations themselves are not hard to describe. Okay, so let's see here. Okay. You'll recall from last time, let me just remind you the last theorem that we stated. So in the plane, the isometry rho sub the origin comma theta has equation rho sub O comma theta of x comma y is equal to the ordered pair cosine theta x minus sine theta y comma sine theta x plus cosine theta y. Okay, so again, we arrived at this result by just realizing that the point cosine theta sine theta is a point on the line that goes through the origin, having a directed angle measure theta over 2 from the x-axis, right? That's how we derive this equation by inserting these constants. Really, the constants were cosine of theta over 2 and sine of theta over 2 into the equation of a line that must go through the origin, having directed angle measure theta over 2 from the x-axis. Okay, and if you don't remember that, look back at your notes from last Wednesday. Okay. So now, this is all well and good, but how do we describe the arbitrary rotation having arbitrary center, right? That is to say, we've described a rotation for arbitrary angle that has center the origin. Now, what if we want to move the center of that rotation? How can we write an analytic set of equations that describe what that rotation does? So here is where we will use the results that we had about conjugation by an arbitrary isometry. Okay, so let's record this. So just this is a new setup for me. I just want to make sure that everything is not off screen for you all. So we can conjugate rho sub the origin comma theta by the unique translation taking the origin 0, 0 to any point h comma k. That is tau sub 0, 0, comma h comma k. Right? Remember, given any 2 points in the plane, there is a unique translation that takes one point to the other. Okay? And this makes some kind of intuitive sense, right? If we conjugate rho sub O comma theta by the translation that takes O, i.e. 0, 0, to h comma k, we produce a rotation that has a center h comma k. So let me just write that in symbols. And of course, let's recall, as long as theta degrees is not equal to 0 degrees, right? Because in the case that theta is 0 degrees, we're just the identity for rho. Okay. So here's something I want you to do this evening. By noting that rho sub h comma k comma theta is equal to tau sub 0, 0, comma h comma k, right? The unique translation that takes the origin to h comma k times rho sub 0, 0, comma theta times tau inverse of 0, 0, comma h comma k, which of course, let me write this in yet another form. This is the same as, what's the inverse of tau sub 0, 0, comma h comma k? What is that inverse? Yeah, right. It's the translation in the opposite order, right? It takes h comma k to 0, 0, right? So let's just rewrite this for clarity, right? So tau sub 0, 0, comma h comma k, rho sub 0, 0, comma theta, tau h comma k, comma 0, 0, and of course, how do I remind me how this first equality is true, right? What theorem am I applying on this equality? Does anybody remember that? Well, all I'm saying is, since I'm conjugating rho by this translation tau, I operate tau on the point 0, 0, which means, what does tau do to the point 0, 0? It takes it to h, k. That's where this equality comes from. Rho sub h, k, theta is equal to the conjugation of rho sub the origin, theta, conjugated by tau that takes 0, 0 to h, k. Okay? Look back at the rules of conjugation of a rotation by an arbitrary isometry. Of course, tau is an isometry, and it takes 0, 0 to h, k. And furthermore, we know that it's even, since it's a translation, right? It can be expressed as the product of two reflections. Therefore, the sign on theta stays the same when we conjugate. Okay? So, by noting the following, what I want you to do for homework is show that rho sub h, k, theta of x, y is equal to, oh boy, this is going to be pretty tight. Okay, so instead, I'm going to erase the top and leave the bottom until you are able to write this down. Okay? So, what I want you to show is the following. You can probably tell what I'm going to ask you. We have an equation for any rotation. We have an analytic form for any rotation that is centered at the origin. And the upshot of this homework exercise is that by the rules of conjugation, the theorems that we've proved about conjugation, you can produce a formula for rotation about an arbitrary center. Okay, so given these hypotheses, make this note. What I want you to do is to show the equation, the following: rho sub h, k, theta of x, y is equal to the constant cosine theta times x minus h minus sine theta times y minus k, all right, plus h, comma, okay, so all this formula is the first coordinate of the output of rho sub h, k, theta, okay, and the second coordinate is just sine of theta times x minus h minus the constant cosine theta times y minus k plus k is your second coordinate. Okay, so here's what I'm asking you to do. Okay, we together developed a formula for rho sub 0, 0, theta. Okay, and you know what a formula for the unique translation that takes the origin to h comma k is. Okay, and by the rules of conjugation that we proved, we know that this results in a rotation of theta degrees about the point h comma k. So in other words, you can come up with an analytic formula for rho sub h comma k comma theta by applying the analytic formulas that you know for these three isometries. Okay, and I've given you the final answer. All I'm asking you to do is verify that that's correct. Okay, so that's really a strictly computational thing. Okay, so let's note these equations can be written in a seemingly simpler form. Can be rewritten as the following. Rho sub h comma k comma theta of x comma y is equal to the ordered pair cosine theta x minus sine theta y plus some number r comma sine theta x plus cosine theta y plus s, where, of course, why do I say somewhat simpler or seemingly simpler? It's because R and S, all I've done is distribute in this formula the cosine theta, a constant, and sine theta, also a constant, to the x and y and constants h and k. And now I have formulas for R and S in terms of h and k and cosine theta, sine theta. So where, in other words, R is equal to h times 1 minus cosine theta plus k sine theta, and of course S is the same type of simplification, h times negative sine theta plus k times 1 minus cosine theta. Okay, so there's a reason that I make this simplification, this line here, where I tell you a arguably simpler formula for rotation about an arbitrary center of theta degrees. Okay. So let's see why. Let me just say that conversely, these equations of a rotation these equations, I'm sorry, these equations of this form must result in a rotation because since R and S, the constants that I gave you equations for here, since R and S and an angle theta, these three numbers uniquely determine H and K. Okay? That is to say, if I give you a value of R, a value of S, and a value of theta, and plug all those in, there's only one possible choice of an ordered pair, H and K, that satisfy that equation, that pair of equations. Okay? And that's because we end up with, if I know R, S, and theta, these two equations I've written down for R and S result in two linear equations in the variables H and K. Okay? So there's a unique solution to a system of two equations which are not the same, right? That's fundamental linear algebra. Okay? So there's something slightly wrong with what I just said. Who can tell me what it is? Anybody have any thoughts there on what the fault in my reasoning was just now? Well, that's okay, because almost every case allows for this to be true, what I just said. The only way things can go awry is if theta is 0 degrees. That is to say, theta degrees is 0 degrees. So let me record that. Unless theta degrees is equal to 0 degrees, i.e. theta is a multiple of 360. Okay. So let's just say if theta degrees is equal to 0 degrees, then what happens? Then what kind of isometry do we get from rho sub h comma k comma theta if theta is equal to 0 degrees? What does the isometry rho sub h comma k comma theta become? Well, yeah, so it's a translation. And in fact, you know, it's most often you might think of it as iota, right? But when we're talking about conjugating, if we're conjugating rotation about the origin by theta, where theta degrees is 0 degrees, and we conjugate by some translation, then we just get a translation, right? So then the conjugate is a translation. Okay. Then, since the only even isometries are what? What are the only even isometries? Someone remind me of that. If an isometry is even, remember our classification of all isometries of the plane, right? There's only 4 things it can be. It can only be a translation, a rotation, a reflection, or a glide reflection. Reflections and glide reflections are odd, which means the only even isometries are translations and rotations. We have the following theorem. We have the following theorem. The theorem. The general equations for an even isometry of the plane, of course, the only isometries that we care about in this course, of the plane, we'll call it alpha, are given by alpha of the point x comma y is equal to ax minus by plus c is the first coordinate, and the second coordinate is bx plus ay plus d, of course, for constants a, b, c, and d. Now there's another condition here, of course, where a squared plus b squared is equal to 1. Okay. So what's going on here? Compare this with the equations of isometries that we have already talked about analytically, right? What is it that is the equation of a translation? Who can remind me the equations of a translation? Yeah, exactly. It's just, as both Keenan and Spencer said, it's just adding some constant to each coordinate, right? So, of course, that agrees with our definition here, right? In this case, for the case of a translation, we let A be equal to 1 and B be equal to 0. That satisfies our condition, a squared plus b squared is equal to 1. Then, whatever the translation vector of the translation is, we let B c comma d. Fair enough. And how about the equation of a half turn? What are A, B, C, and D in the case of a half turn? Right? We already explicitly wrote down the analytic form of the equations for a half turn. If you think about it and recall the formula, you see that, yeah, exactly. Keenan says we have negative x plus 2a for some a, comma, negative y plus 2b for some b, where a and b are the center of the half turn. Okay, so here we just let a equal negative 1, and again, b equals 0, which satisfies our equation, our condition that a squared plus b squared is equal to 1. Okay, and then C and D depend on the fixed point of that half turn. Okay, so this is a kind of sanity check, right? That is to say, all the analytic formulae that we've produced so far, in fact, fit this format, right? For an arbitrary even isometry, right? we have explicit formulae for translations and rotations, and in fact, they agree with this, right? Now, we can expand this to formulae for odd isometries as well, and let's see how. Okay, so let me clear the bottom of the board here. So let's let alpha be an odd isometry. Then for any line L, we can write alpha as the product of sigma L times beta for some even isometry beta. Okay, so that is to say, if you have an arbitrary odd isometry, you can choose any line L and then find an even isometry such that sigma sub L times beta is equal to alpha, your original odd isometry. Okay, so think about this. Verify this claim. Okay, why is it that I can take an arbitrary odd isometry, choose the random line, and then write that isometry I started with as a product of a reflection in that line and some even isometry? Okay, and I'll give you a hint. This is a combination of all those uniqueness results that we had about factoring isometries into pairs of reflections or pairs of half turns. Okay, so just meditate on that for a little bit. All right. So as long as we take this claim as fact, then we can deduce the following result about how to come up with an analytic equation for an arbitrary isometry. Here's the theorem. the general equation of an isometry of the plane alpha is given by alpha of the point x comma y is equal to ax plus, I'm sorry, not plus, minus by plus c, comma, plus or minus bx plus ay plus d. Where, of course, the plus or minus depends on whether alpha is even or odd, respectively. Okay, so this is kind of a surprising result. And of course, what did I forget to say here? The same condition that we had for even isometries exclusively. And of course, we have to have a squared plus b squared is equal to 1. Okay, so as it turns out, isometries are really easy to describe in full. And in fact, we can even put in this notion analytically of parity, right? We just determine whether the second coordinate of what our isometry does flips the sign of these constants relative to this relation. Okay, so how do I deduce this from? I hope it's clear. We made a clear argument of how that's true for even isometries, right? Why is it that I get this result for all isometries? Here's the proof. Remember the last thing I said, that any odd isometry can be written as the product of an even isometry followed by a reflection in some line. So the proof of this is based on the last discussion. Let L be the x-axis. So sigma L of x comma y is x comma negative y. Right? Which meaning that alpha, if odd, I guess I should say, meaning if alpha is odd, we can write alpha as a reflection in the x-axis after some even isometry, which is to say we have a reflection in the x-axis of ax minus by plus c, comma, bx plus ay plus d. Sigma L, where I let L be the x-axis, just flips the sign of this, right? So if my isometry alpha is even, I just have this. If it's odd, then it's this followed by reflection in, for example, the x-axis. So I flip the sign of the second coordinate. That's where we get this plus or minus. Okay? How does that feel? Everybody okay with that? I sent out a couple practice exams for exam 4, and you'll notice that there's a bunch of problems on those practice exams where you're asked to determine what type of isometry an isometry is given some equations, right? So this is kind of how this theorem is how you suss that out, right? You got to compare the coefficients on the variables, see if they're flipped signs of one another. That tells you if they're even or odd. And then compare the coefficients to what you know about the equations of the isometries that we've discussed at length already, right? If that's not clear, hopefully after you do the following homework assignment, it will be more clear. And we'll discuss this first thing tomorrow, okay? So here's some homework from chapter 9. It's not very much. I'll ask you to do 9.1, 9.6, and 9.8. Okay. All right. So with that, we're prepared to start talking about Friese groups, which I have to say, before I started preparing for this lecture, which was in the middle of last week, I was somewhat confused or not knowledgeable. What is a Friese? What is a Friese? What does this word mean? Well, I'll say a little something about that. Don't worry, if you didn't write this homework assignment down, I'll announce it after lecture. I'll put an announcement on Canvas. So let me start by saying that we kind of achieved something by proving Leonardo's theorem, right? That is to say, we made a classification of a certain class of groups, right? We said that any finite group of isometries either has to be of one of two forms, cyclic or dihedral. So now we want to turn our attention to the question of, well, what if we have an infinite group of isometries? is there any hope of doing a similar classification? That is to say, are there a finitistic, easy number of ways to say if your group is infinite and has these conditions, it must be one of the following. So a very difficult problem in general. But when we restrict ourselves to a certain set of conditions that the group must satisfy, not all hope is lost. Okay, so here's what we'll discuss next. And if you recall, if you've been paying close attention since the beginning of this class, remember our goal is to show that there are only 17 types of wallpaper, right? That is to say, there are 17 ways to repeat a pattern such that it fills the plane, so to speak. Okay, so this is like a precursory step to that result. Okay, so let's just begin to discuss the Fries groups. Okay. I'm going to zoom out for a second. I'm going to say something a little broader before we get into the technical details of what a Fries group is and how to classify them. Okay, because this will be useful to us in the next 2 weeks, the final 2 weeks of the course. Okay, so in general, the ornamental groups of the plane are broken into 3 types. And the reason we give these a name is because of historical reasons, because they show up in architecture and design historically well before the advent of group theory as a rigorous discipline of mathematics. Okay, that's why we pay special attention to these classes of groups. So, and there are certain important subgroups of the group of all isometries. Okay, so here are the 3 types. Type number 1, the rosette groups. Which are finite groups of isometries. In other words, by Leonardo's theorem, either Cn or Dn. Okay, Secondly, we have the freeze groups. Okay. How do we abstractly define these? Having a subgroup of translations generated by one translation. Generated by one translation. Okay. And thirdly, we have the wallpaper groups. Having subgroup of translations generated by exactly two translations. Okay, so these are the ornamental groups, right? That is to say, they dictate, in some sense, if you want to think about it historically, these are the groups that dictate the symmetries of the types of patterns people cared about historically. Okay, now from a more mathematical perspective, right, we have this surprising result that any finite group of isometries must be Cn or Dn. Well, consistent with the entire ethos of this course, we should systematically see what can we say if we allow successively more non-finite generators, i.e. generators that will necessarily make our group become infinite, right? Remember, when we proved Leonardo's theorem, our base assumption was that we cannot contain any translations, because otherwise our group would have an infinite subgroup, the cyclic group generated by the translation that it contains. Now, let us assume that we have one translation. What can we say about the groups of isometries that contain exactly one translation as among their generators? Okay, and that's exactly what we get here in case 2, the freeze group. Okay, and it turns out, another beautiful result, there are only 7 possible groups of isometries that contain a single translation as a generator. Okay, now you finally get a window into the result that I told you the first day of this course. We've made some classification result here with Leonardo's theorem in group 1, the Rosette groups. Now, what we'll do for the majority of this week is show that by placing the condition that there's a single translation among the generators, we can show that there are exactly 7 possibilities for those groups. And then, after exam 4, we'll spend the Wednesday after that discussing that there are exactly 17 different types, different groups of symmetries that have exactly 2 translational generators. Okay, so I told you at the beginning of this course that we would build the machinery to support this claim I made that there are exactly 17 types of wallpaper that you can make, right? There are 17 patterns, one of each of which has the 17 distinct symmetry groups that have, or groups of isometries, if you like, that have 2 translational generators. As a warm-up, what we'll do all this week is to discuss how there are 7, exactly 7 of these things that have 1 translational generator. Okay? So that's where we're headed. Okay. So, you know, the first time I learned about this result, I felt very ignorant. I was like, what's a frieze? Is that someone's last name or something? Is that a famous mathematician I've never heard of? What is a frieze? Okay. A frieze is, again, I feel like it's kind of thematic in this course that we periodically come back to some like architectural standard or that design happens to accidentally mean a lot to us, right? A frieze is a band of, usually it's a band of stonework around a building, around the top of a building. Like if you look at a lot of Gothic architecture or early American architecture, there's like a band at the top of the building that has all kinds of shapes and figures in it. Like you'll have like these things or these things. Who knows? It could be anything. It could be like a face. This is called a frieze, right? Etc. This is called a frieze. Why is that called a frieze? I wondered that until I was preparing for this lecture. I was like, well, I better come up with an answer because, I'm beholden to you, the students, and my own curiosity was never enough. So it turns out that a frieze, the word frieze, is derived from the Latin word describing things from Phrygia, which was a nation state in Asia Minor during the Roman Empire. So and these peoples were renowned for their elaborate designs that they put on their buildings. So that's immortalized by this word frieze. So next time you're walking around a city, look up and see. Look for buildings that were built approximately between the 1880s and the 1930s, if you're in an American city. And if you look up to, say, 3/4 up the building, you'll very often see a frieze pattern. Okay? And that's what will be classified, the symmetries of a band of repeated pattern. Okay? Now, obviously, the subject matter of that pattern we want to discount. It doesn't matter what is the motif of the pattern, but rather we just want to classify the ways it can have symmetries, the isometries that fix any given motif. Okay? So let me just say, the essential property of a frieze pattern is that it is left fixed by some smallest translation. What do I mean by a smallest translation? Can anybody hazard a guess as to how we might gauge the size of a translation? This is kind of a seemingly innocuous, but actually kind of profound question. We haven't really talked about the size of anything except in a few contexts. Where have we discussed size? Well, one place we've discussed size or measure is we've discussed it in two places as far as I recollect. There's the we've discussed the length of a line segment. Well, technically three places, right? We've discussed the length of a line segment from which we were able to define the directed distance between two lines that are parallel. And then we've also discussed the directed angle measure between two lines which intersect at some point, right? As far as I remember, those are the only times that we've discussed measurement. Yeah, so Spencer has a great suggestion here. When I say smallest translation, what I mean is the translation whose translation vector that defines the translation has least magnitude. Okay, so it is another incarnation of determining the length of a line segment, right? Because a vector has a start point and an end point, and the magnitude of that vector is just the length, the distance between those 2 points. Okay, so let's record this. So if we're given a translation, tau sub a comma b call the distance AB, the length of tau sub A comma B, right? That is to say that it's just exactly the most basic notion of what you could say for what we can measure, right? Tau sub A comma B is defined by the vector that starts at A and goes to B. That necessarily has a length measurement attached to it. So we call that the length of this translation. Okay, it's a kind of a codified abuse of notation. Furthermore, say that tau sub A comma B is shorter than tau sub C comma D if the distance AB is less than the distance CD, right? Exactly what you would expect for, right, okay. I guess what I'm trying to say is that it might seem odd at first glance to say some isometry is shorter than another one. But when we're specifically talking about translations, we can just use the notion of distance that we have for each vector that defines the translation to make sense of that, okay? And I know at certain times this might seem redundant or perhaps too belabored, but this is what's necessary to make things precise, okay? Okay. So let me tell you a theorem. And just so I have this all on one board at one time, I'm sorry. So Spencer asks, oh, no, sorry. That was your comment from earlier. Thanks, Spencer. Let me just erase and start with a fresh board, and I'll tell you a theorem. Our first tool in characterizing freeze groups. Okay, so let's say if P is a point of symmetry for a set lowercase s, and furthermore, and alpha is a symmetry of S. So remember, what does it mean? Who can recall for me what it means for P to be a point of symmetry? If the set S has P as a point of symmetry, what does that mean? Anybody remember that? Okay, that's fine. If nobody remembers, what that means is that the half turn centered at P is a symmetry of the set S. Okay. So that means, that tells you if a set S has a point of symmetry, that means that it contains a half turn in its group of symmetries, specifically the half-turn centered at P. Okay, and of course, when I say alpha is a symmetry of S, I just mean that alpha is some arbitrary isometry that is included in the group of symmetries of S. Okay, so under these conditions, if P is a point of symmetry for the set S and alpha is a symmetry of S, then I must have the fact that the image of P under alpha is a point of symmetry. Of S. That is to say, the half turn centered at alpha of P is also an isometry that fixes S. All right? And in an entirely similar fashion, if L is a line of symmetry of S, and again, alpha is a symmetry of S, then I bet you can guess what I'll say now. The image of the line L under alpha is another line of symmetry of S. Then alpha of L is a line of symmetry of S. Sorry, that's a lowercase s, of course. Okay. Let's somebody remind me, what is a line of symmetry? I told you what a point of symmetry for a set S is. What is a line of symmetry? Yeah, right. So both Thomas and Keenan say the right thing. You know, you're saying the right idea. The fact is that if L is a line of symmetry of S, that means reflection in L is an isometry that fixes S, i.e. a symmetry of S, the set S. Okay, so what we're saying is the image of the line L under some symmetry of S alpha is also a line of symmetry. That is to say, reflection in alpha of L must also be an isometry that fixes S. Okay, so why is this? This is a nice thing to say. It's something that we would expect. It's what we would hope for. But let's see why it's the case. Okay, so basically, this follows from what we proved about conjugation and the axioms of a group. Okay, so that is to say, let's say, for example, if we have alpha as above and P a point of symmetry, then, well, let me start more fundamentally. Let's say let script G be the group of symmetries. The group of symmetries of the set S. Okay, and then we'll take alpha and sigma sub P, the half turn centered at P, in our group G, right? The half turn centered at P must be in G because I said my assumption was that P is a point of symmetry of S. Okay? So, in other words, by the by the axioms of script G being a group, we know that alpha sigma sub P, alpha inverse, must also be an element of G, right? That's because, of course, G is closed under inverses. And if I multiply anything else that's in G by anything else that's in G, I get an element of G. Okay? So now I know how to deal with a conjugation of a half turn, right? So in other words, sigma sub alpha of P, which is equal to the conjugation of sigma sub P by alpha, is in G. Implies, of course, that the image of P under alpha is a point of symmetry of S, right? That's just what it means to be a point of symmetry of S, that the half turn centered at that point is an element of the set of symmetries of S. Okay? Entirely similarly, alpha sigma sub L, alpha inverse, which is, of course, equal to, because of the results we proved about conjugation, sigma sub alpha of L is an element of G, right? This means that the line, the image line of L under alpha must be a line of symmetry of the set S, right? G is the symmetries, the group of symmetries of the set S. And we're saying that reflection in the line alpha of L is in an element of that group. Therefore, alpha of L must be a line of symmetry of S. Okay, so this is kind of a rudimentary result that we're going to use a lot in the following classification that we'll make of the Fries groups. Okay. So I haven't given you a formal definition of what a Fries group is. I mean, the informal definition is what you should always think of, is what should motivate the work that we do this week. But as is usual in mathematics, you have to have a oftentimes cumbersome definition that is formally laid out so that you can verify things precisely. Okay, so let me give you the formal definition of a Fries group. Okay, definition. A group of isometries that fix a given line C let's call it. And whose translations form an infinite cyclic group is called a Fries group with center C. Okay, so a couple things to note about this, right? So the conceptual definition that I gave you at the beginning, at the outset of this lecture, was saying that Fries groups were those groups of isometries, subgroups of isometries of the plane that contain exactly one translational generator, right? So I've encoded that in a formal way by saying that I get an infinite cyclic group, right? Remember that a group generated by a translation must be infinite, right? And what does it mean for a group to be cyclic? It means that it has one generator, right? So in other words, this is equivalent to saying that I have an infinite cyclic group of translations. All the translations in a Fries group form an infinite cyclic group, means that that group, that subgroup, is generated by one translation. Okay? And furthermore, just again, an annoying piece of terminology is that so far, anytime we've talked about a center, we've talked about a particular point. Note here that a Fries group has a center, which is a line. Okay? So if you think back to that crappy drawing I made at the top of the board at the beginning, the center of that group is the line down the center. Okay? So again, it's context dependent what a center is, right? If we're talking about half turns, we're talking about a point. If we're talking about rotations, we're talking about a point. If we're talking about a Fries group, the center is a line. I know that's annoying. I'm sorry. I'm just the messenger. Feel free to shoot me if you want. Okay? So with that, we're out of time. Tomorrow, we'll begin to classify the 7 different types of Fries groups. Okay? And I expect that to take us about 2 days. And then each time we classify another Fries group, we'll draw a schematic of a pattern that has that as its group of symmetries. All right? So please let me know if this isn't working. I'm trying my best to provide during this time where I can't be at Northeastern right now. If this is not working for you, please let me know. Please email me, and we can spend some extra time talking about things that were unclear. Okay, so I apologize for any inconvenience, and I'll see you all tomorrow. Okay.